Hi class, welcome back to our lectures on quantum field theory, and this is the continuation of chapter 10 part 2 of electroweak theory. And I'd like you to read the books on quantum field theory of Michio Kaku, Mandon Cho, and F. Gross. You'll find there more details and even more discussions on this particular topic. So we're now going to discuss about weak mixing angle or Weinberg angle. And by the way, before I forget, I this I have discussed about the field B mu and W mu, W mu 1, 2, and 3. Actually, I told you that B mu is the field associated with the U1 symmetry, and W mu 1, 2, 3 is the field associated with SU2. However, I also make a statement in the previous lecture that B mu is the field for photon and W mu 3 is the field for Z particle. But class, actually there's mixing between B mu and W mu 3, and that mixing makes the A mu, which is really the field for photon, and Z mu, which is the field for the Z particle. So that was just to simplify the discussion, but now that we have the mixing angle or the Weinberg angle, we will now introduce to you the mixing between B mu and W mu 3. So we start with the definition where we define the relationship between the coupling constants GB and GW in this particular equation. So the ratio between G, W, and GB is just tangent theta W, where theta W there is called the weak mixing angle or the Weinberg angle. And this is the reason this is the reason why there is mixing between between B mu and W mu 3, and the mixing is actually given by this. So A mu is a mix between B mu and W mu 3, where B mu is multiplied to the cosine of the Weinberg angle plus W mu 3 times the sine of the Weinberg angle, and correspondingly for Z mu, this negative B mu sine theta W plus W mu 3 cosine W theta W. So actually you can write this as cosine theta W sine theta W negative sine theta W cosine theta W B mu W mu 3. So you can also write that in matrix form. So now it's written down here where the matrix is just the rotation R theta W So the gauge field mu is nothing other than the electromagnetic vector potential which couples the photon to the theory. So there is now a link between the photon and the three particles of SU2. Now we'll go to symmetry breaking. Before, we have already described theory with two leptons, the electron, its corresponding neutrino, and the 4-gauge boson. So so far all the particles described are massless. Now we introduce mass into the theory, and of course this will be generated by symmetry breaking, which we've learned in the previous chapter, with chapter 9. So if you want to review that lecture, you can also search back the lecture in YouTube. So in here we introduce a Higgs field that will enforce the gauge bosons to acquire mass, and we introduce a field for the photon, so that a unified picture of the electric interaction can be presented. So following the method we've done previously in chapter 9, introduce the Higgs field as a scalar spin zero field. However, this time we have to introduce a two-component object, or two-component this is like a spinor, but of course this is the field, and each component of the field is a complex scalar field, and it's written as this one and this one, phi A and phi B here. So in this case, the Higgs field is composed of 4 scalar fields, and if you do this operation, this one, so you will have phi A adjoint phi A plus phi B adjoint phi B. So this is actually coming from this one here. That one. So if you put in the definition of 10.24, you'll be able to get this expression. The Higgs field carries a charge of the weak interaction, and this hypercharge is given by positive 1, and the isospin is given by the value 1/2 for the Higgs field. So note that the SU2 transformation is given by previously by equation 10.16. So we have this transformation, and we exploit this gauge freedom to simplify the form of the Higgs field. And this can be done by insisting that each of the angles are functions of space-time. So this is it means alpha j is a function of x, which is just the space and time. Why is it? Because the theory must possess local symmetry, and we have to find the invariance, local invariance of the theory. So the gauge freedom can actually help us in choosing this one as a function of space-time in such a way that our phi A is 0 and our phi B is a fluctuation on phi 0. There's a fixed value of phi 0, and then you have a fluctuating field around phi 0, which is just the Higgs field over square root of 2. This is just a normalization constant. You can actually disregard it, but this is just placed there to simplify everything later on. So our phi, this is now the form of the Higgs field. So we have this one. And of course, phi sub o there and h of x are both real functions. I mean, phi sub o is a constant there, where it allows the symmetry to be broken, because it will of course break the symmetry, because you will be choosing that phi sub o as the minimum value. So instead of taking the ground state to be 0, we take it to be this one. So from this we have already broken the symmetry, and the Higgs field will make its appearance later on in the Lagrangian 10.20 in many ways. So if we go back to 10.20, we can go back up to here. Yeah, we will be able to make an investigation on this particular Lagrangian, part of the Lagrangian. So going back, the Higgs field will be introduced through a potential here, and the kinetic energy terms and the interaction terms that couple the Higgs field to the electron and gauge bosons. So then it will give the mass to the gauge bosons. So going back to equation 10.26, where we use the phi to write our potential. So here, by the way, this is plus this term here is plus phi sub o. It's there's a mistake there. So our phi adjoint phi would be this form here. And so the potential is of course given by this. So if mu square is greater than 0, then the minimum of the potential is located at phi equals 0. And for mu equals mu square is less than 0, the symmetry will be broken, and this will cause the Higgs field to attain a vacuum expectation value. So what is then the new minimum? So we apply again a derivative to the potential V with respect to phi. So we will get with our V being this one, we get the derivative with respect to phi as this one here. So here actually you still have a phi plus here, which cancels with this, and then with our phi being this one, we would actually get this one would look like phi mean square for this one here to be equal to negative mu square over 2 lambda. So we can define this one to be the minimum, our phi sub o, which is just this one here. So we would now have our phi g. We set this to be this one. With a mass of square root of negative 2 mu square. From here, this is supposed to be the mass term, this one. So the mass would be negative square root of 2 mu square. That's the mass of the Higgs field or the Higgs particle. So for the mass of the lepton, we will now investigate it. So a Dirac Lagrangian consisting of the left and right-handed fields with mass m is written as this one. And for here, the mass term in the Lagrangian is of the form which is just m negative m psi l psi r plus psi bar l psi r plus psi bar r psi l. This is just the third term in the Lagrangian, where m there is a scalar, a number, and not a function of a function dependent on space-time. In the Weinberg-Salam theory, an interaction term known as the Yukawa term is introduced. And this interaction term is of the form this one here. And this interaction term couples the matter fields to the Higgs field. The Yukawa coupling GE defines the strength of the interaction between the Higgs field and the electron-lepton fields. So we have here the interaction term, and we look at each term here. So psi bar L phi, we have this one, and then your phi is this one. So your psi bar L phi would be this, and then but if the gauge choice that led to the form of the Higgs field in 10.26, where the upper part of the matrix is 0, the neutrino term drops out, so our psi bar L becomes this. And using your psi r, which is this one, which we have set initially, since we set that there are no right-handed neutrinos, so we can find that psi bar L phi psi r would just be equal to this. This will now replace this one, the first term there. I mean this term. Now for the next term, which is just this one. So this is just 0 E bar R, and then we have our adjoint of the phi, which is just this one, and then our psi L given by this. So our psi bar R phi adjoint psi L would be given by this. So again, the neutrino term drops out because it has to multiply this one to this one, so it will just become 0. So our interaction term will be simplified to this. So from here, which is just equal to, if you substitute our earlier result, this would just be this term plus this one here. So as you can see, you have this term, but you have this Hx here, the Higgs field, and this one here is the is a term where the coefficients are constant, so this could be the mass term. And so if you look back this one, so the mass term must be corresponding to this term, and the mass must be constant here. So you would be able to get this expression as the part of the Lagrangian that contains the mass of the leptons. So these are the electron and the right-handed and the left-handed electron. And so the mass would just be equal to the Yukawa coupling times the vacuum, value of the vacuum. Here, the interaction of the Higgs field with the electron leaves the neutrino massless and gives the electron the mass defined in 10.34. However, in experiments, neutrinos have masses, non-zero masses, but they're very small, and that this is a suspicion that the theory is incomplete. And so, of course, today neutrino studies are very popular, and they are actually making some detectors in say for example in Antarctica to detect neutrinos and measure its mass. So anyway, we will not talk about that, but yeah, it's found out that experimentally neutrinos have indeed very small masses, and this has some repercussions in the death of a star in the universe. So yeah, we'll just leave that discussion for later. Now we will go to the masses of the gauge bosons. Now let's calculate the Higgs mass, the masses of the gauge boson through Higgs mechanism. So they will acquire masses through the action of the covariant derivative on the Higgs field. So again, as you can see from here, even the W plus and the W minus are combinations of 1 and 2, W mu 1 and W mu 2. So these are the combinations of the field, just like in A mu and Z mu. But here you have you don't have a mixing. The mixing is imaginary, unlike A mu and Z mu. So the covariant derivative then is given by this. The second term is associated with the U1 symmetry, and the third term in the derivative is associated with the SU2 symmetry. And then now we apply this derivative to the Higgs field. So we have here d mu phi to be given by this. Now the tau, vector tau, that W mu, we have here, of course, we have 3 taus, tau 1, tau 2, and tau 3, and our mu, W mu 1, W mu 2, and W mu 3 given, distributed respectively to the tau 1, tau 2, and tau 3. And so we will have this as the matrix, the product of tau and W mu. So we have this term, this one here. So it will now be expanded to this one by multiplying the Higgs field phi. Now for 10.37, if you look back, this one, the first derivative would just give you this one, only this, because phi sub o is a constant, and the next term would be given by this one supposedly, and then you add them all together. So this one is the second term, which is given by this. So by the way, the adjoint of this one is just given by this, and this is just the row matrix adjoint of this column matrix. This one is also a row matrix. It's not two terms being a difference of two terms, but this one is a row matrix which has an element, first element, and the second element is this one, which is just this one. And you also have the signs here are opposite because it's already the adjoint, and this one also should be opposite. I mean, no, this one and this one, and of course this one, and yeah, this one. So if we multiply, the first term would give you this, and the second term would give us so this is the product of the second term, so this one, and of course this one here. So it will give us so this one will be multiplied, this one will be multiplied by this, and it will give us GW square over 2, and then this one, the matrix would be multiplied to here, and then it will give us so here we have 2, and so our denominator will just be 2 because this is supposed to be 4. So we have W mu negative, W mu positive, and then we have here the square of that, and we also have GW square over 4, and then we have this one, and of course the square of this. Now we have a cross term here. We're supposed to have a cross term, which is um, given by this one and this. So we will have this one here, and the second cross term would be given by this. Yes, and of course the final term would have to be the product of this one and this one. So you will have there GB square over 4 B mu times the square of this term. So I mean of that element. So you will have here this expression. Now we would have to ignore terms that include the fields, because if we just are interested with the mass, we just are interested with the terms that are with coefficients of constants. So for boson fields, we look for the terms this one here, and yeah, if we use the Weinberg angle, we just convert B mu with this and our W mu 3 with this one. So keeping only the leading terms in this expression, which is the only term that gives a scalar number, if we look up here, again so this is just this one here. Yeah, we just look at this term because this does not include h here. So we have now this one. If we put all together the terms, we have this one, and of course this one will be given by this here, and of course that one, the W mu 3. And then if we expand, we will have how many terms? One, and then we have 1, 2, 3, 4. So we have this one multiplied to here, and then this is an interaction term of A mu and Z mu, and this one, yeah, is also an interaction term. And this is now the mass, determines the mass of the Z, mu. And of course, W mu. So we now have the next term for the cross term here. This one. So that will be given by this. So with the expansion of W mu 3 and V mu, we will have this one, this expansion. So this is just an algebraic result that we can put together later. And for the second cross term, we have this one. So as you can see from here, we have we can actually cancel this one and this one, and of course this one and this one. What else is negative? No, they add up, I mean, so they add up in this case. So anyway, in the final term would be this one, and so you will have these terms. So now you combine everything together, so you will have by the way, we ignore these terms because this is an interaction term. We're just supposed to have this term to get the mass. So in this case, you have for A mu, A nu. Then you have if the mixing angle is 0, then this would be 1, this would be 0, and this would be 0. So here your scenario would be a pure coupling to the W boson and no coupling to the Z boson. If it's non-zero, then there is coupling to both fields. So this is actually the diagram of how you would see cosine theta W and sine theta W. We can replace that here in this terms. So if we replace that, this will actually give you this one here as this one. This quantity here will now be 0, and so therefore your A mu would be a massless field. So in this case, this would have to be your photon field. And for the Z field, of course, again, we discard other terms other than A mu A mu, Z mu, Z mu, and W plus W minus. So for here, you will have this one. So this is now the mass of the Z. And similarly for W plus W minus, our mass of MW is, I mean, the mass of the W boson would be this one. And of course, we can also find this identity here in terms of the masses of W and Z. And the theoretical bounds on the masses are actually this one. So experimentally, the masses of W are exactly, I mean, exactly greater than this. Theoretical bounds. If I'm not mistaken, MW is around 60 GeV, while MZ is around 80 or 90 GeV. So this also tells us that the measured masses indicate that the sine square theta W is equal to 0.222. Or our theta, this is theta W is 28.1. Now, the ability of the Weinberg-Salam model to predict the masses in this way is what earned its discoverers the Nobel Prize, giving confidence to Higgs mechanism as a valid meaning for adding masses to the model, despite the fact that the experimental observation as yet eludes. However, these things are being studied right now. So, as a summary, the Weinberg-Salam model combines leptons and gauge bosons into a single Lagrangian that has SU2 cross CU1 symmetry. The original formulation of the Lagrangian is for massless particles, including a massless electron, massless neutrino, and for massless gauge boson. However, spontaneous symmetry breaking using the Higgs mechanism breaks the SU2 symmetry and gives rise to masses of the electron and the gauge bosons W plus and W minus, and Z sub 0 that mediate the weak force. The symmetry breaking also includes the photon field in the model, unifying the electromagnetic and weak interaction into a single Lagrangian. And so finally you have the electroweak theory. So you can also answer this very simple quiz. By yourself. So that's it for this part of the lecture. So we're now finished with chapter 10. Let's move on to chapter 11 in the next lecture. That's all, class. I hope you learned something today.